Welcome one, welcome all. So, we are doing the streaming yet again, and for anyone that hasn't been a part of the stream before, if you don't know the sort of thing I'm doing here, this is going to be a little bit different. What I've been doing for this last week, literally every single day for the last week, at varying amounts of time, normally it's 1 hour, I've been recording myself doing LeetCode questions. And once I finish doing the stream, I then upload that video to my YouTube channel, and that YouTube channel is where you can find all the previous streams. And this gives viewers or subscribers the ability to watch these at their own pace, go through the questions at their own pace. And I figured that at the end of every week, at the end of all of this lead coding that we've been doing, it might be good for us to revisit some of the problems that I've saved, do sort of like a weekly roundup. That's what I'm considering doing here. One of the things I'm particularly excited about, and apologies, I have to sneeze. Wow, that's going to sound great, especially with this new thing that I just bought. One of the things I'm particularly excited about is the purchase of a new microphone. I decided to get a Blue Yeti microphone, and I hope it makes a big difference for anyone that has been listening to me in these past couple of days. I heard one of the more recent streams that I did, and I'm really happy with it. It just sounds way better than the mic that I was using on my headset. And so I'm still learning about gear and these mics and whatnot because I've never really owned a mic of my own. So I ended up going with the Blue Yeti. If anyone, if you're having problems hearing, or if the quality of the audio is a little bit off, or if you have any suggestions for things that I can do audio wise, please let me know, because I'm very open to learning sort of like the best tricks to get the audio delivered in the best way. So today, like I said, the stream is going to be a LeetCode weekly roundup. So, like I said, the previous LeetCode streams that I've been doing are they're centered around just going through every single question on LeetCode. That is exactly what the intent is with I guess my other main streams. And if you've been following me, as of today, we've done 54 questions, and we've been doing this for a week. So I think we're making great progress. That's 54 questions in a week, doing about an hour a day, going through them, talking about them. I think it's pretty neat stuff. So normally what I do is I'll go through a couple of these, and there have been some that I've saved to my lists. So if I open my lists here, apologies for the brightness. I don't think, the extension I have doesn't make this dark, and I guess their dark mode doesn't go into their profile sort of section here. So you see here we have all these different questions. I probably forgot like why I even saved some of these questions to begin with, but I think I'll go through them now, and we can sort of talk about them all together, and we'll see if we can learn a thing or two about them. So this first one here, the range sum of Bst, I think the main reason that I wanted to go through this one, and let me just make sure. I think I saved this. I think I see, like, I know what the right answer is now, and I had never figured it out until the day that I decided to stream this. So normally what I would do for this question is, it wants us to traverse this tree, and for any value of the root that exists within the range that it gives us, it wants it to add it to the sum eventually. Now, one of the things that I didn't take advantage of the first time I went through this question was the fact this was a binary search tree. So what I would do is just do any of the, traversal flavors, hit every single node, and construct my sum that way. But as you can see here, I started coming up with an algorithm to say, well, if we know that we have a binary search tree, it's a very good idea to try and use that to our advantage. The fact that nodes on the left are less than the current node and nodes on the right are greater than the current node. It will help you a lot, and it'll make the time complexity a lot better. So I remember one of the issues with my algorithm here being was that this function I created with var in range accepts a num, low, and a high. I wasn't passing these numbers into in range, right? So if in range root.val, it really should be, let's see, if in range low and high, I should pass low and high here. And then here, I should also pass low and high. I think just doing this gave me the right answer, but let's run it now and see for ourselves. So 32 and 32. For anyone that's been watching me for a while, I used to have premium, and still to this day, I just want to spam that run code button because I'm so used to doing it. So I think this should give us the right answer here. Okay. So one of the things you have to consider, and I think here it's like, if it's in range, do this. If not in range, if root.val is less than low, I think what I was able to do before, like what if I just say, if not root, if in range, yeah, I think this is fine here. If it's not in range and root.val is less than low, yeah, I was happy with this answer here. Really what we do is now, instead of going through every single array, not every single array, every single node in this tree, we look at all these together. We look at these in a very methodical way. And then what I ended up doing here was a sort of, I guess we can call it, would it be post-order traversal, where I look at the children first and then do something with those values, give them back to my parent, and then return that value. So if we look at this here, so say, okay, if the range here, if this is in range, okay, cool, and now let's return the left one. Now the left one's not in range, so we know that like we can't go any further down this way, because the left one's already lower than the lowest one, presumably. So we might be able to go right. So by going right here, we can essentially start the whole thing over, and now we say, if this is in range, cool, keep visiting it in this fashion. So by doing it this way, you see that already here, we did not have to traverse this tree right here that had 3 inside of it. And you can imagine for a tree that's a larger size, has more nodes in it, this is very effective. This is going to make it so that at different points of our algorithm, we're like halving the problem, right? So it gives us this more log of n solution instead of the n linear solution I was doing before, where I was going through every single node. So this is something I was very happy with. I forgot what question this was in the whole list or where it shows up, but I think this was the first question that I realized that me actually talking about these problems on stream, and hopefully you all listening to me and just seeing how I sort of reason about it, it not only helps me, but I really truly hope it helps the viewers. So that was the first one here. Convert binary number in a linked list. Yeah, one really cool, interesting thing that I saw from here that I noticed was part of I saw it in the solution once I had already come up with my own answer. So given head, which is a reference node to a singly linked list, the value of each node in the linked list is either 0 or 1. Yeah, it'd be nice if we can just do this in a single pass. I'm going to have a drink of water, so 1 second. So it's not entirely clear to me right now how we can do that, but I think that's what we should think about during this stream right here. Let's see. We have a 1 and a 0 and a 1. And I want to multiply. All right, so like anytime if I do a bit shift, like let's think about bit shifting, right? Let's just open this up here. Let's think like if I have a 1 and I shift it, if I shift that by 1, I get 2. Oh, but let's also save x to 1. So shift this by 1. I think we could do, is that an operator? 4, 8. So every time we shift it by 1, it's like increasing. I guess I don't want to say what, increasing by the exponent. It's doubling itself, right? Which is exactly sort of like what we want here somewhat, because we're doing 2 to the power of something else, and it's either going to be 1 or 0. So if it's 1, maybe we can push it, else we don't need to. I think we can do that, right? Like we have a 1, 0, 1, and we know we're going to have, actually, let's do that. Like if I can start with the 0, right? So let answer equals 0. Can I zoom in here? I just want to show you guys what I'm doing here. Let's say let answer equals to 0. And if I get to the first node and it's a 1, can we actually just do answer equals, or I guess answer shift by that bit? I was really hoping we'd get 1. That would have been nice. That seems weird. Wait. If I left shift it by 1, that gives me 0? How do we, let me revisit what it means to left shift bitwise. I'm going to increase the gain on this mic a little bit. And if it's too loud, let me know. I just really want to make sure that everyone can hear me all right. Again, this is the first, like today is literally the first day I've ever had any sort of mic to be able to record myself. I know it's better quality, but I just need to make sure that you all can actually hear me. So the left shift operator shifts the first operand the specified number of digits to the left. So, oh, we wanna shift the current one by, so if we have 5 and I shift it by B, can I shift it with a 9 to the left? Like we have a 0 and I want to introduce the 1. How can we, or can we add the 1 and then shift it? Let's see. If we do answer equals answer or 1, that gives us 1. Okay. And then we get to the next one. So when we get to the next one, maybe we shift it. Answer equals answer over by 1 to get to 2. And then we do answer equals answer or 0, which that doesn't seem right. Or we get to the next one, and now we do answer again equals answer to the left of 1, or left shifted by 1. And then we do answer equals answer or the root value, which is 5. Will that work for any case here? I always want to shift it by 1. Let me see if we can, like, let's open up an Excala draw here. You can see I've been sort of doing other stuff here on my own. Let me remove my whole space here, and let's try to come up. Let's just write some stuff out here. So let's say we have, where's the text here? Okay, 8. Make this extra large. Let's say we have 1. Come up with something somewhat easy. So 1, 0, 1, 1. Right. So what is this? This is 1 plus 2 is 3. This is a 4, and this is an 8. So 8. That's 11. That took me a long time to calculate, but this is an 11. Okay. So the answer here, let's say this, that's 11. So how could we get there? Like if I started at, I'm gonna have an answer, right? We're gonna have an answer to begin with, and that's just gonna be 0, right? So in the beginning, I look at the first one, and I say, okay, let me OR. Maybe I can OR the current value to my answer, something like answer equals answer or the root dot val, right? And then answer equals answer left shift by 1. I'm thinking maybe we can do that. Let's see what that does. If I open up DevTools here and I kind of just do that, let's say answer again is equal to 0. We have answer, I think I can do 1, so that's 1. And then answer left shift over by 1. Cool. And now what if we OR it by 0, and then we do left shift again, we OR it by 1, we do left shift again, and then we OR it by 1. Now, OR it by 1, do we do the left shift again though? No, but this is it actually. This is sort of the answer, right? This is using bitwise manipulation instead of having to rely on the stack, and we can do it in a single pass. So I think this is pretty interesting. I like this sort of stuff a lot, but we're going to figure it out. I think what happens here is we can't do, like, maybe I should only ever shift to the left if I'm not at head dot. If I'm not, okay, I like this. Here we go. Let's just say, let's go back to here. I'm gonna actually completely refresh this answer. And let me make this a little smaller so everyone can see. Let's say decimal equals 0. Now we wanna do it while what? So while, I guess we can do while, if we do while head dot next, we could do while head dot next, and then at the end we can just OR it with the, we can just OR it, and we don't have to shift it because we only want to shift it while head dot next. So let's see if we can do that. We can do decimal equals root dot val and answer left shift by 1, head equals head dot next. All right, so we'll do 0 or 1, which is 1. We'll shift it over, so we get 2. Now we go to the next one. We are with 0, which is nothing. We shift it over. Now we get 3. We go to the next one. We OR it. Oh, no, we get, let's see, we OR that. We get 4. Now we come here. It's already head dot next. But what we could do is we can just say decimal OR equals head dot. Yeah, let's not do, let's say runner equals head. That's one thing. I don't want to modify the head pointer coming in. So while runner dot next, decimal equals runner dot val, runner equals runner dot next. And then here we can just say runner dot val, return decimal. I feel like this might work. Let's see, answer, of course. We never had, I don't know, I think answer was coming from, answer was coming from when I was on Excalidraw. 5 and 5. Let's see, 0, well, runner dot next. So that will just give us that. Let's see, I like this so far. Okay, phenomenal. This is exactly why I do the LeetCode weekly roundup. This is the first video in the series, but this is exactly why I'm revisiting old questions, because the first time I did this question, let's compare the different solutions now, right? This is linear time complexity with constant space. We're just purely relying on bitwise manipulations here. Very, very cool stuff. I wonder if there's, it's like hard to find. Oh man, there was a really nice DigitalOcean bitwise. Can I see, like, I'm trying to look at my history of things I have found in DigitalOcean recently. Wait, recently closed? No, I want to see. Oh, are these just tabs? Okay, install Node.js, custom types, prototypes. Is that really all I have? Okay, wait, that's not it. I'm looking for something in my history of an article I found related to bitwise manipulation that I thought was really good. Interesting use cases for Oh, Blog Rocket. Yes, this one. This article was really nice. I'm going to save this to the list of questions. That's like something else I'm trying to do now. I'm trying to keep a list of compiled links, like a list of links that we visit during the stream that I would then add to a description on the YouTube video. That way you all can sort of gain something from these links. But yeah, this is a great solution because before, if we look at previous submissions, let's look at like one of these older ones here. Yeah, you see this one. This one I had to create like another function inside of here, right? Like a function within a function. So this is a closure, right? Because it does keep some, it keeps some grasp of the outer variables, and because of this, well, actually, wait, it's not returning. It doesn't actually live. This isn't actually a closure because it doesn't return anything that then lives on after this function ends. After this function ends, the rest of it ends. So it's just using scope rules here, but it's a little more complex. We have to rely a little bit more on the internal stack. That is implicit space that's being taken up, right? The stack has to be built and then unwound. So I think that using bitwise manipulation here might be considered a little bit clever and harder to see during an interview setting, but it's one of those things that hopefully you get an intuition for and you can see. One thing I've realized, bitwise manipulation is very good when you have a problem set with a finite scope. Like if you're dealing with lowercase English letters, it's similar to how to like, if you know you're dealing with lowercase English letters, you can create a fixed size array instead of having to generate like a hash table or something. I feel like bitwise manipulations are really nice when you're dealing with unique values and you just need some way to keep track of them. So I think this is pretty cool. So yeah, very happy that we were able to look this up. Okay, so create target array in the given order. Let's see. Yeah, this one. Well, I was pretty happy with the way I did this one. Let me see how I can even. Oh yeah, no, this is just a brute force one. I think the way that we can make this better. So what was the brute force idea for me here, right? Literally, I just have an array, and if when I entered a value, there's nothing there, I just entered it. If when I entered a value, there's already something there, then I start shifting everything to the right. But I was doing this sort of shift operation, even if there was nothing there, if that makes any sense. So let me see what we can do. So I did for let I equals 0, I less than index length. Let's see, for let j equals nums.length minus 1, target array. Oh yeah, I literally went for every single one. I really shouldn't do that, because if they're, yeah, are these all gonna be positive numbers? Maybe I can fill this up with -1. And I can say if, yeah, like if target array, let's see, I have my nums and I have my index I. If target array at index I is equal to -1, right? Then here we can just say target array at index I equals nums I, else we can do our shift. I think this is a simple sort of optimization that we can do here. Try to make all this stuff line up nicely. But obviously it didn't line up nicely. What am I missing here? Why does this look so weird? Is this actually, maybe it should just look that way. I don't think so though. There you go. Else for, this goes there, that goes there, that's fine. This goes there, this just goes in the next level. Okay, so the way that I see this is, previously I was always doing this like even if it was the first time I ever added something there, I was still always going to the end of the array and shifting everything over, even if I didn't have to. But what if I fill this? Why did I choose -1, by the way? I chose -1 because if I look at the constraints, I see that all these digits will always be positive. Like, I can't choose another positive integer, like a 0, because then if I entered a 0, then I'll never know if I have never entered it in there before. Hopefully that makes sense. So I chose -1. There aren't any negatives in these indices, right? And there also aren't any negatives in the nums. So if it's a negative, I've never been there, just entered the value right away. Let's see what this gives us here. 0, 4, 1, 3, 2. Let's go through all the different test cases. Zero, 1, 2, 3, 4, and then 1. Okay, sweet. Now I'm very curious. The one I just ran now. Okay, 723. If I keep running this, 84. What I really want to see is I want to see a trend downward for runtime. Okay, so that's pretty good, right? If we keep going here. Yeah, this was 96. But already we have 2 in this 69 range, which is good. That means it looks like there's a trend, although now it's going back to 36. It could just be dependent on where this code is being run. Like, I'm sure LeetCode has some virtual infrastructure and some cloud, and maybe that computer's just hogged up right now. Okay, so yeah, one small optimization, like I said, we made here is before ever checking to see if I have never entered something there before, I was doing the shift every single time. So this saves us a little bit on computation. We don't have to constantly be shifting elements over if we don't need to. Okay, sweet. Count good triplets. This one is crazy. I already went over this one today in one of the streams from earlier. Let me go ahead and open up. I just want to show you here. So in, I believe, today's stream earlier, did we not do, oh, maybe, oh, I think I talked about it briefly, but we didn't actually like go over it, maybe? Yeah, good triplet, here it is. So this question has the crazy like to dislike ratio. A lot of people don't like it. Just like looking through it, I think the best way of doing it is just pure brute force. I generate every single triplet and just apply this constraint against each generated triplet. And if we can, or if that triplet passes the constraint, then I increase the amount of pairs. That's really all I'm going to say about this question. I'm not in love with this question, but the hints kind of say as much. Loop through all the triplets and count the ones that are good. I might be able to make some slight optimizations, but I'm not sure that the question is of high enough value for me to even want to do that. So I'm going to move on to the next one for that. Sum of all odd length arrays. This one is a doozy. This is a very, very good question that honestly, I don't think it's an easy. Because of this, I might save this one for last here. Let's see what we can do here. Order stream, and I should keep track of the ones that we've already done. So I'm gonna remove range sum, convert binary number, create target array, count good triplets. Okay, design an order stream. I don't know why I put this one on this list. I think I did because it's just a very annoying question. They try to supply an animation, but I think it just makes it more tricky. Really, like, the best way to answer this, or the best way to look at this is like, man, I don't even, like, you insert the value at the pointer they give you, like 3 CCC, so we put a CCC at 3, and if it if the value that you're entering it into matches the pointer you're currently at, so like here, right, number 1, like the next one's 1 AAA. So we're like, okay, 1 matches A. So as soon as that happens, now we start going forward as long as there are valid values, and we just concatenate all the values in between. I probably didn't do this question any justice in that explanation right now. And honestly, it's also a heavily, I mean, this one's even worse than count good triplets because it's just a terrible question. So I'm sorry if you ever have to run into this question. I don't think it's worth it. But I'm happy that we at least got a chance to do it. And I went through it in one of my streams. If you want to take a look at it, then you'll be able to find it there. Cool. Let's go to the next one. Let's delete that question and never think about it again. Check if 2 strings are equivalent. Okay, this one. Oh, okay, yeah. I would like to give this one a shot because I think the real algorithm, the real point of the algorithm here comes from being able to, instead of just saying if, you know, word 1 join equals word 2 join, being able to have multiple pointers to traverse to both of these lists at the same time. And I think we can do that if we have, let's say, A, B, and B, C, A, B, C, and A, B, C. Let's see how we can traverse this. Let me put just give me a second. I'm going to put on the air conditioning in my home. It's a little bit stuffy in here. All right. Let's think about what we can do here. So we can have 4 pointers, and let's think about the different pointers we can have here. So we can have an I, we can have a J, maybe like a K, and an L. So, well, actually, the J doesn't go here. The J is kind of like, you know what? It's time for Excalidraw. So ABC and ABC. Okay. So let's get our drawing tool out. Let's do A, B, C, and A, B, C. Okay. I'm going to space these out more because I need to show you what it means, or where I think each of these pointers should be. Okay, so let's imagine we have, like, we're gonna need a pointer for each sort of string in each one of these arrays, right? So like our I can be there. That's a crazy looking I. Make this a little bit bigger, give it like a nicer color. So let's say I is going to be this one here, and then J is going to be this one. But then on top of that, we need to have K be like, K is going to be the index of the first character here, and then let's say L is going to be the pointer of the second string. So we need 2 pointers that correspond to the strings themselves, and then 2 other pointers that correspond to the index in those strings. And there's like a couple rules that we need to follow here. So let me see if we can, instead of create, like I was trying to create crazy index names earlier, I'm just gonna do let I equal 0, let J equal 0, let K equal 0, and let L equal 0, just to make it easy. Now I think we want to iterate each of these pointers. Right, so a couple things. 1, iterate these pointers as long as they are shorter than their word lengths, right? And then if at any point they don't match, return false. Right? As soon as they don't match, return false. Now what happens if one of them goes out of bounds? Right, so if one goes out of bounds, you increase the word index and reset the character index. And you want to essentially do this. Let's see, if one of them goes out of bounds, that's fine. Are they both going to be the same length? They're not both going to be the same length. Oh wait, word 1 dot length, word 2 dot length. Okay, so I guess if at any point, let's think about this. Because is there a case where one of them can be, like if one of them is out of bounds, but there's still space in the other one, which would mean that's true. We can do it while both are below. Let's try that. Let's make it so that while I is less than word 1 dot length and k is less than word 2 dot length. So I and k are going to be sort of like the pointers that point to the word themselves, but not the characters. So let's see what we can do with this. Right, so iterate these pointers as long as they are shorter than their word lengths. Now, if at any point, let's see, iterate these pointers as long as they are shorter than the word lengths. If at any point they don't match, return false. So if word 1 at I at j not equal to word 2 at k l, then return false. If at any point they don't match, return false. And then here, let's see. I might have a drink of water, so just give me a second. We've compared them, right? We've compared them, and they are equal at least. So now let's increase the character indices, right? J++ and L++. If J is greater than or equal to, let's see, word 1 at I dot length, then we increase I and j equals 0. If L is greater than or equal to word 2 at k dot length, then we do I, j, k++, L equals 0. This is 4 different pointers, right? Because, well, let's just give this like a shot, right? Let's give this a shot here. Let me just write these out. And what I'm going to do is I'm going to put the word index on top and the character index on the bottom. Make some space here. H, I, J, K. And we'll have L right here. Okay, let's look at our algorithm here. So if I is less than word 1 dot length, which it is, and k is less than word 2 dot length, which it is, if word at I, j is not equal to word at k, l, return false. That's not the case. So we'll do j++, and we'll do L++. So note that j is still in the bounds, but L is equal to the length. If j is greater than or equal to word 1 dot length, which it's not, but L is greater than or equal to word 2 at k dot length, so we say k++, now k goes to the second one, and L now becomes 0. So now we're here. Now we go here. If word I, j not equal to word 2 at kl, return false. They are equal. So we'll say j++, which now makes that out of bounds, and L++. If j is out of bounds, we do I++, and j is 0. L is fine. We compare. We don't return false. I++. And no, not I++. We do j++ and L++. If, let's see, if j greater than or equal to word 1 I dot length, right? I++, k++. Okay, so what happens at the end? Both of them need to be out to be, so I guess if at any point, if I is greater than or equal to word 1 dot length and k, I only want one of these to be true, right? Only one can be, if one of those is true and only one, then we should return false. So I think we can maybe use an exclusive OR here. And j, no, k is greater than or equal to word 2 dot length, return false, return true. I'm using exclusive OR because the OR it can still be true if both of these are true, but if both of these are true, then we see that it's fine. So only if one of these, like if I was out of bounds, but k, if there was like still other characters here, right, and k was here, so it's not out of bounds, then that wouldn't be good, right? Because we would want both of them to be out of bounds. And the XOR would make it so it's just an exclusive OR, which means only one of those things is true. So if I is greater than or equal to word dot length, or k is greater than or equal to word dot length, return false, else at the end, we should be able to return true. But I mean, we'll let the algorithm decide. Let me open this so we can see. Actually, I don't even think we need that. We get true and true for these two cases. And now we have a ton to go through, so here we go. True, false, true, true, false, true. Looking good so far. Let's see. Okay, 52.57. Very cool. So I mean, I'm very, very happy with how this is all going for me right now. And I really hope that for anyone watching, they're gaining a lot from this, because if you all know, if you watch the streams earlier in the week, these are questions we struggled with. These are questions we were unable to do, and now we're able to do them. So if you've been following along with me, I truly hope that you've gained a lot from this, because I certainly have. And now we're able to see how using 4 pointers here, we were able to get our answer. Right? So this makes it so it's in place. We're not, right? Because I think before, I don't even remember how we did it before. Oh, we did join. Right? So we had to use extra space to be able to create those resultant arrays. Because if I look at, let's see, string join JavaScript time complexity. What is time complexity for string concatenation? Or array join. Let's see, array methods, push, pop, shift, splice, sort, iteration, map, reduce, bonus, sum. Okay, so join is not in there. So browser string optimizations. Okay, join is almost 2 times faster. Better go with string concat. So I would really like to see the time complexity of common array operations. Does this one work? Join. Join is not there. I'm going to assume that join is O of n. So we went from a linear space to constant space. Right? We're not creating any extra space here. And we're still having to traverse to every single word. So it's O m by n. The overall time complexity for time would be O of m by n, right? And then the space would be constant. We're not creating any new space to be able to go through this. So that's how we benefit on the space. So can we see, if we look at submissions here, runtime, memory, somehow my latest one uses more memory. That's never a good thing to see, right? Just when you think you nailed it, hit it out of the park, you realize that you could have actually done better. 41.9, 42, 42.1, 19.75. Well, at either rate, it's another, at any rate, I guess is the way to say it, it's another way of solving the question. 4-pointer technique, multiple pointers, always good practice to get. So that's pretty neat. So let's remove this one here. Let me work on this one, because this one also, at one point, I was making this question seem crazy. A couple of streams ago, I was going on this whole thing of how this reminded me a lot of a medium question I attempted a long time ago related to how many different locks you can generate, or the shortest path to like get from one lock combination to another. I kind of thought this was it, but now thinking about it, I think all we need to do is just iterate through both of these, and we're going to flip on some bits or we're going to leave some bits alone. So if we think of both of these, like we're starting at 10 and we want to go to 7, right? So we're starting at 1 0 1 0 and we want to go to 0 1 1 1, right? So the only way to get there is we need to toggle this 0 and toggle this 0 and then toggle this 0. So that's 3. So I think the way, like if they're not the same, if these bits are already the same, we don't need to do anything with them. And we know that we can get them, we know they're the same if doing XOR on them, right? Because if we think about like the truth table for XOR, what is the truth table, right? If we have 0 0 0 1 1 0 1 1, XOR means exclusive OR. So it's only going to be 1. It's only going to be 1 when it's exclusively a single bit that's turned on. Right? That's what that piece means right there. So we know that like if the bits are different, then we can do something. So really we should check to see if XOR gives me back, if XOR gives me a 0, right? Then we don't need to do anything with it. So let's see if we can get that piece first. I think I can say, and let me just make sure I'm not just like, right, like 5 XOR 5 is 0, 5 XOR 6 is 3, 1 XOR 1 is 0, 100 XOR 100 is 0. So just testing out different things here. So we can say const is same bit. But what do we do here now, right? We need to get access to both of those bits. But here we can say bit 1 and bit 2. And we can return bit 1 or bit 2 equals 0. And I don't know if I need any sort of parentheses around here, but let's do that. Is same bit. Okay, now how do we get a bit now, right? I want to get each individual bit. So don't even worry about these together. But if I'm at a certain position, let's say my mask is 1. If I have a bit mask of 1, if I do 1 and 1, I'll get 1. If I do 1 and 0, I'll get 0. So to get the bit, I just have to AND it with the current mask. Right? Like if I ANDed this with 1, anything else that's 1 will be off and a 0 will be 0. If I instead did this, what do we get here, right? Everything will still be off. We'll get a 1. So let's also do the math on this. If we do 7 and 1, we should just get 1. Okay, if we do 7 and 2. So 7 and 2 is going to give us 2, right? Yeah, so I think it's that. I know it's on. Well, let's do one for the case that it's off. Let's go up here. If I do 1 and 0 here, it's not going to equal. All right, so if 10 and 1 is going to give me a 0, 10 and 1 will be 0. So 7 and 2 does not, so if 7 and the number does not equal the number that I gave it, right? So const get, let's do const get bit. And let's say if I want to get a bit, I can just pass in a number and a mask, right? Here we can say return, we can return the num and masks. So if num and masks equals to mask, then we can return 1, else we return 0, right? Because if the num, it's only going to be 0 if they're the same. So 0, 0, 1, if I do 7 and 1, I should get 1. 7 and 2, I should get 2. 7 and 3, I should get 3. But then once I do 7 and 8, we'll get 0. So I think this will work, and I feel like these are mainly the two pieces that we need, because now we can say, we can continue doing this while, we can continue doing this stuff. We want to go from start to goal. So while start is not equal to goal, why don't we do something like while start is not equal to goal. Let's keep track of our steps. And what is it that we'll have to do here? Well, start is not equal to goal. All right, so now let's go and figure it out. Or do we just have to count the places where the bits aren't? Wait a second. I don't need to get anything. Don't I just need to count the places where the bits are different? I think that's all I need to do. And then, let's see. How many places is the bit different from the current one? What would be the nicest or the easiest way for me to do that? Is same bit and get bit. Maybe there's probably a better way. But let's see. Get bit, and then set bit. We need to also set the bit, right? So set bit equals num and mask. And we return, well, I don't want to return anything here. All I want to do is say num equals, yeah, set bit, so I can just set it with the 1. Okay, let's see, 1 mask equals 1. This is going to be very interesting. Let's start in the beginning. So let's get bit 1 equals get bit of start and 1 mask. Const bit 2 equals get bit of start or of goal and 1 mask. All right, so I'm gonna get like remember if 7 and 1 is equal to 1, then we just return a 1 for the get bit. If equals mask, we return 1, else 0. Okay, so if they're not the same bit, so if not is same bit, bit 1 and bit 2, we want to change start with our mask. You can say steps plus plus, and then mask shifted over by 1. So let us try that out. Well, I think that's 1 1 1. Okay, so let's get our 1 mask. Start not equal to goal. The start 10 is not equal to 7. We got 0 and 1, right? We got the bit 1 and bit 2. They're not the same, so we say start or the mask. So now this makes this 1, right? And then we shift this over by 1. So this becomes a 0, this becomes a 1. And now we get the bits again. Start is not equal to goal. If same bit, if is not same bit. So well, let's do the same thing again. We got 1 here and 1 here. They're the same bit, so we don't do anything. We just immediately go to the next one. 0 1 0. Get the bit. They're different bits. Start has this mask here. We go last one over here. 1 0. They're not different bits. Ooh, wait a second. If they're not, because now start does not equal goal. So wait a second. 1 0. It wasn't the same bit. So I don't want to just OR it. Do I just want to? So should I just toggle it? Should we just toggle it? How can I just toggle a specific bit? If I do an XOR with a 1 and it's a 0, that's gonna invert everything. Yeah, toggling a specific bit. Let me go back to that article I was reading earlier, because since we're all learning here, I think this is the point. So let's see how to toggle a bit. Turning off bit, checking for set bits, turning on bits, toggling bits. Toggle to 1 while every other, okay. In bit masking applications, commonly used for toggling or flipping certain bits. This is based on the fact that for any given bit A, the bit remains unchanged when paired. So A with 0 equals to A. Oh, the bit is always toggled when paired with the corresponding bit. Oh, is that because a 0 and 0 will be, a 1 and a 0 will be 1, so that'll just leave it alone. A 0 and a 0 will be 1. Unchanged when paired with a corresponding 1 bit. Okay, so I think we could do this. Because now we say const bit 1 and bit 2. They're not the same. So now we do start. Start equals start X order mask. So 1 and 1 is 0. 0 1 1. So is this gonna work? Return steps. Start mask. Oh, 1 mask. And then 1 mask. Three and 3. Of course, I ran it too soon. Let's see what we got. 3 and 3. Okay, so looking good so far. Can we get it here? 25.66. Okay. Yeah, I don't know why I was making this question out to be way harder earlier. Although I think all this function stuff up here can probably, I can probably make it a little bit more condensed. I probably don't really need to do that. I mean, I could just inline all these really. Get bit, start, and one mask is same bit. Would that help if I inline all of them? I don't know. Oh wait, set bit. I never even used set bit. I mean, let's try it out. Num becomes start and mask becomes one mask. So let's see what we can do here. Start and one mask. Oh, and now instead of one mask, I can just do mask. So let's do start. Okay. And then same for here, except now we have goal and mask. So no longer have get bit. Let's do same bit. If not, let's put all that stuff inside of here. No more same bit. So let's see. Oh, I think I still left one mask down here. I just did some inlining that could help us. 3 and 3. So I'm surprised it's still running pretty slow. $54. I'm very curious to see. Let's see discussions. One-liner XOR count set bits. Yeah, so we just need to get, okay. Yeah, we only needed to count the set bits. That's all we needed to do. So I was sort of right there. My thing was mostly figuring out, like, how do I know when to stop? One-liners, have a look. Integer bit count. Number of different bits is the required bits to flip. To make start and goal same, we can efficiently calculate them using the XOR operation. Is there something that's a little more, I don't want to see start and goal, count equals 0, while XOR is greater than 0, XOR add XOR minus 1. I wonder if this is there a way to see, yeah, I want to look up a good article for like counting set bits in a number, something like this. I just really want to understand how that works. Okay, so we solved this one. Happy with that. Now we have these two left. Build array from permutation. Zero array based permutation. Solve it without using extra space. Can we solve it without extra space? Probably. I thought there was maybe, how can we do this? Build target array. Build array from a permutation. Is this kind of like, I don't know why I have a feeling in my head that this is almost, can I just follow this thing the whole way? It wouldn't be like cycle detection or anything. No, I don't think it's cycle detection. I think it's more, given a zero-based permutation, build an array answer of the same length, or answer of I. Let's do this. I'm gonna take a quick 30-second break just to do some housekeeping. Like, we've been going over a little over an hour right now, which is totally fine since this is our weekly roundup. I don't really have a set time for how long this will take. I just want to quickly talk about, for the people that are watching this right now, how is it that you might be thinking, hey, this is cool, I find this helpful, how can I learn more, where can I find more of your videos? And what I do with all these streams, including this one, I'll upload this one as soon as I'm done here, is I upload all these to my YouTube channel. So every single stream that I've created since last Saturday is on YouTube. You can watch all these streams. Each one of these different videos has a list of every single question that we've done, and it also has chapters, so it makes it very easy for you to go through them. I have a little channel introduction here that tells you the intent of the channel, why I think it's helpful for not just you, but also me. You know, it sort of gives you like an accountability partner and a buddy. You can watch the videos and do the questions at the same time, or you can do the questions first and then come back and watch the video. And hopefully, you know, you'll learn something. You'll see me make mistakes. You'll hear me struggle. And I think that's always good to watch someone go through like doing these LeetCode questions. It's been a lot of fun doing it, and I really want to give back to the community. So if this is something you're interested in, I'll drop the channel link on the stream chat. And if you wanna link up with me like personally, just feel free to start a chat with me on Reddit, or you can, you know, you can. I guess that's like a good way to do it. Just hit me up on Reddit, and I can link up with you there, and we can talk a little bit more about it. On the Reddit is a link to my Discord and also my blog. You can see it up there on the top right, where the banner is for the YouTube. That'll give you some more places that you can find me if you're interested in this sort of thing. I'm going to continue doing these streams for as long as I can. I just invested in a microphone today because I'm serious in this, so I'm really hoping the audio is coming through, and it's been great for everyone watching. So without further ado, let's get back to our questions here. Just wanted to do some quick housekeeping. Let me have a sip of water. All right. Let's see. We have 2 left. The sum of all odd length subarrays is pretty tough. Build array from a permutation. This one's weird because they want to do it in what? O of 1 space. So does that mean that I cannot create, like I just cannot create any other? Can I not create any other array at all? Because sometimes people say, oh, the output array isn't considered extra memory. I don't know if that's the case, because this here seems too easy. The follow-up is really what seems hard. So 0, like if I want the 2, I go to the 2, that becomes a 1. If I go to the 1, that becomes a 2. The thing here is the thing at 5. The thing here is the thing at 3. But like, as you notice, I can't be doing this and overriding these values at the same time, right? Like, let's say the thing at 0 becomes the thing at 0. That's fine. The thing here becomes the thing that's at 2, which is the 1. So if I put the 1 here, and let's say I save the 2, okay, what if I say, okay, the thing at the 1 becomes the thing at the 1? Are all these unique? All the elements are distinct. So what if I say here, the 1 at the 1 is already a 1, so maybe I should look at my temp. Okay, that's cool. Then I go to 5, the thing at the 5, the thing that's here should be the thing located at 5. So this becomes a 4. And let's see, this becomes a 5. Now the thing here becomes the thing that's at 3. This becomes a 3, and this becomes a 4. So now we've just sorted the array. That's not what they want. That's not what I'm supposed to do here. Although it's a cool way of doing it. But nums equals nums at 0. Nums, yeah, right? 0, 1, 2, 4, 5, 3. 0, 2, 1, 5, 3, 4. So how was it that we got there? Right, because the thing nums 0, nums at 2, nums at 1, nums at 5. Yeah. Like this becomes the thing at 2. So this should be 0, 1, 2 for sure. This becomes the things at 5. This becomes a thing at 3, which was 5. So maybe before I change this, like this is 5, 3, 4. Maybe I'll save the 5. I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 3. I'll take the thing that's here at 3, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at 4. I'll take the thing that's here at 4, and I'll take the thing that's here at set this here. Then I go to the 3 and I say, hey, like, did I already, if I've already been there, let me look at my temp. So that becomes a 5. Maybe I'll put my 3 there, and then this becomes a 3. So am I just always saving the temp before moving it? That wouldn't always work though. 5, 0, 1, 2, 3, 4. Let's see this next one. 5, 0, 1, 2, 3, 4. So the thing at this index becomes the thing at 5, which means I'm going to replace it with a 4. Okay, let me save my 5. The thing that is here becomes the thing at 0, which isn't 4, it's whatever my temp was. So maybe this is, and that's 0. The thing here becomes the thing that was at 1, which is a 0. Okay. Thing here becomes the thing that was at 2, which was the 1. No, but this, see, this is one of those contrived examples where everything just fits nicely with each other. I think that's what it is. I can try that out and see. I don't think that's the answer, but let's see. I mean, there's no harm in trying, right? Because we can do, let's see, let temp for let I equals 0, I less than nums dot length I plus plus. I want to get the number let's see, what would temp be to start off with? I don't think it would be anything. Yeah, I want to get the index, const index equals nums at I. Let's say temp equals nums. No, temp, yeah, const index equals the nums at I. So I want to go to, yeah, I want to go to the array at that index. Well, temp will equal nums at I, and nums at I will equal nums at index. And then we go to the next one. We look at 0, index, temp equals nums I. So we can just say if temp, let's say temp equals undefined. If temp equals undefined, we can do that. Else nums at I equals temp. And maybe we should do this. Does that work? Let's see. So we get the thing at 5. Const index equals nums at I, which would be nums at I equals 5. That's the index. If temp equals undefined, which it is, nums of, okay, no, then nums at I equals temp, which that's not right. Oh no, that's fine. If temp not equal to undefined, then we do this, right? Else nums at I at 0 equals, oh, I think I just got myself in a bit of a loop here. Yeah, let's outline each one of these. This becomes the 5 for that second example. nums at 0 is 5. Now I want to go and get the thing at 5. Say const num equals the thing that's at index, right? Const index equals 5, const num equals nums at 5, which is 4. Okay, because temp is undefined, I want to set nums at I to equal num. Okay, cool. Temp is undefined. Temp should now equal nums at I. Nums of I equals num. Temp equals undefined. But then after that, we always want to set temp anyway. So should this just be temp? Temp equals nums at I. No, because I'm still going to be doing some setting. I always want to get it before this is so strange. I think what I did was I messed up the algorithm here again. When I'm looking at, oh, it's not so much of, okay, the num, here we go. The num is only going to equal the index the first time. So we can say temp equals undefined. We can set it to nums at index or temp. So let's comment all this out here. Let's go through this again. So const index for this first one, nums at I, nums at 0 is 5. Then I say num, temp is equal to undefined, so I go to 5, that's 4. Now I can say nums of I equals num. So if we do this whole thing again, let's see where we are here. We're here at I. Index is nums of I, so index is 5. Num equals temp equals to undefined, or nums at index 5, num is 4. Nums at I equals 4. Oh, but wait. We didn't save temp. That's the weird part. I don't know why it's being so difficult for me to do that. Nums of I equals num. But maybe we should say temp equals nums of I. So let's say here temp equals 5. Nums of I equals num, which is 4. Now we go to the I. Index at I equals nums at I. If temp is equal to undefined, or num is equal to temp, which is 4. No, num equals 5. Temp equals 0. Nums I equals 5. So let's see what this yields. I mean, if this works, it'd be a little bit strange. Undefined. Nums.length. Nums I. I have a lot of code written here. Oh, I didn't actually return nums. Let's return nums here. Let's see what we get. 002153. So completely off there. Let's see what we get for the next one though. Because if this one's off, Yeah, 450, 1, 2, 3. So it only worked for the second one, but not the first one. I think this, again, this second example here is just like a very contrived example to what it could be. I'm going to table this one for a second. Let's look at this one, the sum of all odd length subarrays. Yeah, what I did here was I generated every odd length subarray, but can we look at can you solve this problem in O of n time complexity? Yeah, this definitely isn't O of n time complexity. All odd length subarrays. I really want to think that some sort of prefix sum would work. Where we have 1, 5, 7, 13, and 16. So I know maybe why do we know all these will show up? That's tricky. I might give myself, I know I said we can go on forever. I might give myself another 10 minutes since we've been going for about an hour and a half, and it's almost midnight. It's actually past midnight here where I'm at, so we need to get some rest. But let's see if we can do some more stuff here. How can we generate all odd length subarrays in a linear time complexity? Linear doesn't mean one loop. We can have multiple loops that are not nested, though, that are sibling loops. Some of these, though, there's a very clear pattern if you draw it out. Some of them pyramid, and others don't. If you have, we can write some stuff. Actually, there's a notepad here, isn't there? Yeah, can this be helpful? So we have 1, 4, 2, 5, 3. We see a 1 once, a 4. We see all these numbers once, right? Actually, let's do it in increasing order. If we have a 1, we just see a 1 once. If we have 1, 2, we see a 1 and a 2, and that's it. No other odd length. If we have 1, 2, and 3, we see a 1 once, a 2 once, and a 3 once. Oh, we can't. Okay, yeah, we can scroll here. Nice. We see a 1, a 2, and 3, and then we see a 1, a 2, and a 3, right? Because we see each one individually, and then we see the entire one, which gives us 1, 2, 3. Well, let's say we have 1, 2, 3, 4. We see 1, 2, 3, 4, and then we see 1, 2, 3, and then 2, 3, 4. Now let's say we have a 5. 1, 2, 3, 4, 5. We see a 1, 2, 3, 4, 5. We see a 1, 2. We see a 1, 2, 3. We see a 2, 3, 4. And we see a 3, 4, 5. But we also see a 1, 2, 3, 4, 5. Now let's see if we have a 6. I think 6 will hopefully give us 1, 2, 3, 4, 5, 6. We see a 1, 2, 3, a 2, 3, 2, 3, 4. Oh, I messed all this up. We see a 1, 2, 3, a 2, a 3, and a 4, a 3, a 4, and a 5, a 4, 5, and a 6. And then we see a 1, 2, 3, 4, 5, and a 2, 3, 4, 5, 6. So, oh, I just hit the mic, so hopefully that wasn't too abrupt of a noise. So if we look at this, right, for let's see, if it's 1, 2, or 3, what's the length of all these? This is length of 1, this is length of 2, 3, 4. As soon as we start at 4 is when we get this pattern, right? And we see that each one of these is included some amount of times. So maybe if it's less than 3, if it's 1, like what's 1? Okay, 1 divided by 1 is 1, right? 2 divided, well, yeah, definitely 1. 2 divided by 1, that's 2. 3, no, maybe it shouldn't be 1. Maybe it should be 1 divided by 2 plus 1. 1 divided by 2, 0.5. If we floor that, that's 0 plus 1 is 1. 2 divided by 2 is 0 plus that is 1. 3 divided by 2 is 1.5. That's 2. 4 divided by 2. Okay, that's 3, but then why do we start there? It's almost like I'm trying to figure out. I feel like anything over 3 is going to have this pattern, but what does it go up to? 1, 2, 3, 4. Oh, wait a second. 5, 6. Oh wait, 1, 1, 2, 2, 3, 3. Is it just a multiple? Like if it's 1 or 2, it's just 1. If it's 3 or 4, you start at 2. But then that doesn't become a 3 in the middle. Okay, let's do 7. I would expect to have a 4 on the outside for 7. So 1, 2, 3, 4, 5, 6, 7. We have a 1, 2, 3, 4, 5, 6, 7. So here we're gonna have a 1, a 2, a 3, a 2, a 3, a 4, a 3, a 4, a 5, 4, 5, 6, 5, 6, 7. We're also gonna have a 1, 2, 3, 4, 5, a 2, 3, 4, 5, 6, and a 3, 4, 5, 6, 7. And then we're also going to have a 1, 2, 3, 4, 5, 6, 7. So it is 4. So this is some notes we have to take, right? If it's 1 or 2, let me close this here. So 1 or 2, we're going to start at 1. 3 or 4, we're going to start at 2. 5 and 6, we're going to start at 3. 7 and 8, we're going to start at 4. Now what's the relation here? Is it just like how many, like, if the array is 1 or 2, 2 divided by 2 is 1, 4 divided by 2, 6 divided by, okay, so I think both of these, like what is 8 divided by 2 is 4, 7 divided by 2, 2 divided by 2 is 1, ceiling, okay, 4 divided by 2, 6 divided by 2. So maybe that's how we just figure out the numbers in the, like I'm thinking some weird formula maybe where like either number, whether it be 7 or 8, we can do math.ceil of r.length divided by 2. So 7 divided by 2 is 3.5. If we do a ceiling, we'll get 4. 8 divided by 2 is 4. Ceiling is 4. 1 divided by 2, that'll just give us 1. That should give us where we start. That can give us where we start and how many of each digit we're going to have. And then maybe what we can do, we know that if, let's see, we're only going to increase it here in the middle if it's greater than 3. I guess we can increase the multiplier. So let's see what we can do with this information. I'm going to comment all this out. So let's get multiplier. Let multiplier equals math.ceil of r.length divided by 2. So if it's less than or equal to 3, that would just equal 1 for this. So 1. Oh, and that, oh no, yeah, that's fine. Those sum of all odd length 1 plus 2 is 3. 1 times 1 plus 2 times 1. Okay. If it's 3, it would just be 3 divided by 2, which is 1. Ceiling, just apply that across the board. So we can say if r.length is less than or equal to 3, then we can return r.reduce. Let's do r.reduced of ac and val. Here I'll start with 1. And then here I'll return the accumulator plus val, which is 1 times multiplier. All right, so it's going to be, let's see. So 1 times 2, yeah, 1 times 2 is 2, that's 2, and then 2 times 2 is 4, 1 plus 4 plus 9. So let's do 1, 2, 3, and let's see what they give us. If we do 1, 2, 3, is it going to be 9 plus 4, 13, 14? Is it going to be 14? And 12. Expected 12. 3 times 3 is 9. 2 times 2 is 4. Plus 1. Expected 12. The sum of all these. 1 plus 4. 1, 4, 2. Oh, it's the sum of all the odd length arrays. So if we do 1 plus 2 plus 3, that's 6. Right, but we're counting all these. 1 plus 1 is 2. 2 plus 2 is 4, 6. 3 plus 3 is 6. So maybe it should just be, yeah. 1 plus 1 is 2, but 1 times 2 is 2. 2 plus 2 is 4. Ac plus val times multiplier. Oh, is it just because, yeah, I put this thinking that that's going to be, okay, 0 is the ac. Okay, 12, 12, that's fine. Now, so here, we can start at either side. So sum equals to 0. Let's start equals 0. Let end equals r dot length minus 1. And let's look at our notes here. I guess it can always be, so they're going to be the same. Yeah, so we can do while start is less than or equal to end. Let's do sum plus or equals r at start, or we can just do sum, yeah, let's do one at a time. Sum plus or equals r at start times multiplier. Sum plus or equals r at end times multiplier. start plus plus end minus minus, and then return sum. Let's see if this works. 12 and 12. Oh, it's the same one we had before. This would be great if it worked. 51 and 3 and 66. Oh, so it's the first one that I'm off. Let's see why. Oh, wait a second. We need to increase our multiplier, right? Yeah, multiplier plus plus. 68, 3, and 66. So 14253 is 5. So we do 5 divided by 2 is 2.5. So ceiling is 3. We do sum plus or equals plus plus, and then oh, and we're doing it, yeah, we're doing it twice. The last one should only ever be, oh, this is crazy. I mean, I get what I have to do here. Like, if they're equal, what do we do? Well, start is less than end. Do that. Okay. And if they're equal, we do something else. We should only count that once if they're equal. I don't really want to like remove it from there, but I know that's definitely the issue. Maybe depending on the length of the array, if it's even, I want to do one thing. If it's even, I want to do less than. And if it's odd, I want to do less than or equal. Actually, no. And then it'd be nice if we also knew the peak. If I knew the peak of these, I feel like we're making progress here. It's just needing to know how we get to that peak right there. It's an odd length array, so we're only going to count the middle one twice. I mean, I could do something nasty and just subtract. Like, I can say here, if r.length, if start less than or equal to end, we can do the sum here. And here we say that if start equals to end, we can say sum minus or equal this and return sum. This is nasty looking code. I'm not happy with this. I'm not very happy with it, but we made it this far, so let's see what happens. Okay, so that didn't work. I feel like we're close, and there's probably an easier way of doing this. I'll table this for now. And I think since what we should do is, this was our weekly roundup, I think this should still be on this list. And you know what? We'll revisit them in next week's weekly roundup. This is probably the longest stream I've ever done. Actually, about the same amount of time as the longest stream I've ever done. So I'll wrap it up and say, I really thank everyone that watched today. I hope you were all able to learn something. This is just a weekly roundup. Tomorrow we'll go back to doing the LeetCode questions that we've been doing so far, and we're almost to 100 questions done, so I think that's pretty neat. If any of this stuff interests you, if you're looking for a way to be held accountable, you want to progress in your LeetCode journey, you want to go through every single question like I did, I highly encourage you to check out my channel that I've linked on the stream chat. If you want to learn more information, feel free to DM me or chat me up on Reddit, and I can tell you more about it, and I really hope to see you there. I'm going to start uploading this now as soon as I finish, and you'll be able to watch this roundup on the YouTube channel at your own pace, and we can just have a good time. So thanks again to everyone that watched. I'll be here again tomorrow starting the next LeetCode stream. Hope you guys all have a great rest of your day, and take it easy and happy coding.